Hello, I'm Bianca.
And I'm Paloma, and you are listening to the Climate Press.
A podcast where we aim to bring together climate science with public understanding and action.
Today on the show, we are joined by experts in paleoclimate, Dr. Lauren Gregoire, who is an academic research fellow in Earth System Modeling, and Dr. Ruza Ivanovic, who is a lecturer in climatology, both from the School of Earth and Environment at the University of Leeds.
In this episode, we will be talking about ice sheets and glacial periods of the past, present, and future, and how these relate to climate change.
Hi, Ruza, Lauren, how are you guys? Welcome
Great.
To the show.
We're good. Thank you for having us.
Yeah, thanks for coming on today. So can you, to start us off, can you tell us a little bit about what are ice sheets and how do they form?
Yeah, so ice sheets are very large masses of ice. We're talking about kilometres thick that rest on land. And currently there are two main ice sheets, one in Greenland and one in Antarctica. And in fact, Antarctica, even though it rests on land, some of it is even below sea level. And those are very prone to potentially collapse.
Mm-hmm.
We know this very well in theory, but actually in practice, we don't know how much a threat it could represent. But it could be a very big threat for future sea level rise.
They're important because they're on land. So like anyone who has had a gin and tonic, you notice when your ice cube melts, the level in your glass doesn't go up. So ice that's already in the ocean is not as important for sea level rise, but ice is on land, it's going to directly cause sea level rise. So that's why the ice sheets are so important.
And do the ice sheets that are below sea level have the same impact as the ones that are above the land in sea level rise?
Almost. So the part that is below sea level will not rise sea level, but there's so much above that it will. And also because they rest below sea level, they are more subject to very rapid retreat. So they currently represent a very large...
They're vulnerable, essentially. They're more vulnerable to changes in things like the ocean and internal mechanisms of ice dynamics, which we'll probably talk about a bit more later.
Yeah, or if you want to, you can tell us a little bit about that now then, like why would they be more vulnerable?
So if you think about Antarctica, for example, there's a current going all around Antarctica, and that can bring very warm waters just underneath the floating part of the ice sheets, and can start melting it away, which can push the ice sheet a bit further back. And particularly when the bed of the ice sheet reclines towards the interior.
So that's when it's sloping down towards the interior, is that right?
Yes, okay. That's right. Then it can become unstable. Okay. And so a little bit more warm waters that arrives near to the ice sheets can trigger a very rapid retreat.
Okay.
And therefore really rapid.
So it's a bit like a runaway
change.
bit like a runaway feedback then, is that what you mean?
Yeah. So it kind of starts retreating a little bit, and then it's unstable, so it carries on.
Right.
Retreating.
Kind of like opening a floodgate almost. Like once it starts, it's hard to stop almost that process.
So we've got observations that suggest that today it's starting to happen in parts of Antarctica. But we haven't had that kind of mechanism happen yet in the recent past. We've not been able to observe ice sheets for a very long time, and they've been very stable up to now.
Okay.
But we do know actually that in the past there has been instances of instabilities in the ice sheets, so very rapid changes in the ice sheets.
So Lauren, I have to confess, I'm a climatologist. So can you tell how long is the record for ice sheets?
Oh, we're talking about a couple of decades of observing the ice sheets. They're in very remote places, So we've got our best observations are from satellites. But yeah, we've only got a couple of decades of these observations. We've got some from sort of very early expeditions down in Antarctica, but they're very patchy observations. So yeah, very, very short.
Yeah, so that's why we like looking at the past, because that gives us this extended record where we can see these kinds of changes, different ice sheets. So glacial cycle, when you went from a really cold state to a warm state like today, it's typically sort of around 100 or 120,000 years. So that's quite long. So obviously we don't have satellite observations that go back thousands and thousands of years. So the last time we were in an interglacial state, nice and warm like today, sea level high like today, was about 120, 130,000 years ago. And then slowly the climate started to cool. Mostly because of changes in Earth's orbit around the sun. So it changed the balance of radiation, the balance of energy reaching the surface of the planet. And things started to cool and these big ice sheets started to grow. That happened progressively until about, let's say, 20,000 years ago, we reached what we call the last glacial maximum. So that's when the ice sheets were at their largest, the climate was at its coldest. And during that period, we had huge ice sheets that don't exist anymore today. So there was Antarctica, which was bigger than today, Greenland, which was a bit bigger today, Iceland, we had some small ice sheets over New Zealand and Patagonia, but the really big ice sheets were the Eurasian ice sheets, so over a lot of Europe, including the UK. Not quite Leeds, didn't quite reach Leeds, but kind of surrounded us. And
some trap here.
Well, Lauren might be able to tell you why the ice didn't quite reach Leeds.
It was a bit too dry, I think.
There you go. The dry climate of Leeds.
Yeah.
Hey, come on. We're the right side of the Pennines, at least.
I agree.
And then there was also this huge ice sheet over North America, covered a lot of Canada, stretched down kind of over
the whole of Canada was covered in ice,
we think. And kind of came down into the US over, well, present-day US, over the Great Lakes.
And you say we think, like, so how do we know? I mean, you were talking about using satellite images for today's.
Yeah.
But how do we know this kind of past record
well,
in this detail?
These ice sheets are so powerful that they leave behind traces of their flow. So you can really see scours in rocks. And they even erode so much of the rock and the soil and push it right to their front. And they leave what we call moraines, so they're really like little hills, really.
Huge piles of debris.
Yeah.
Earth, which, you know, you maybe would just think it was a hill if you were out walking, but actually, you know, to the trained glaciologist's eye, you can see that that's evidence that there was ice flowing here, ice that was tens of meters, hundreds of meters thick. And as I said, in places, and as Lauren said earlier, in places over the UK, could have been kilometers thick. So you can just imagine if you were standing on the ground and you were looking up on a nice kind of sunny day, few clouds in the sky, that's the cloud base, that's how thick that ice sheet was. Yeah.
That's incredible.
Pretty high.
They really shaped the landscape. And so that's how we know how big these ice sheets were.
It's quite variable. Obviously, you have fast places where the ice flows quite quickly. They're called ice streams. And then in the interior of the ice sheet, right in the middle, at the top of ice mountains, say, in the middle of Antarctica, in the middle of Greenland, you have very slow flowing ice.
Like millions of years. Or just 1 centimeter per year or something like that.
Well, I think...
Well, this is just curiosity.
Yeah. Meters per year in the fast-flowing parts.
Okay. But to give you some perspective, in the slow flowing parts,
100.
That's where we have our records from ice cores. So people have been out into the middle of the ice sheet where it's very thick, and they drill, and you get a cylindrical core of ice. You pull up. Be very careful. You do it. Keep it very clean so you don't affect the chemistry of the ice. You do it slowly. It's technically very difficult because you don't want the hole to refreeze. You need to keep getting that ice out. but they go and drill those where the ice sheet is at its thickest and slowest flowing, because that's where we have the records that go back hundreds of thousands of years. So Greenland ice core record goes back to the last interglacial period. So I said before, it's about 120,000 years ago.
Wow.
And the Antarctic record is much longer. Actually, we currently go back 800,000 years.
Amazing.
So it's about 7 or 8 glacial, interglacial cycles.
Mm-hmm.
And the Europeans currently are starting on their efforts to extend that record even further back. So to go over 1 million years, maybe even 1.5 million years. So almost double the length of the record that we have. And although that ice core record doesn't tell us directly how the ice sheets changed in those places, it tells us a lot about how the climate changed.
Mm.
And that's at an incredible resolution in terms of time.
Mm-hmm.
So some of the records you can even see annually resolved climate. As you go further back in time, it might be more like decadal, but still for a climate change, and for a climate change we're talking about decadal kind of scales, then you can imagine what a valuable resource that is. So we can see how temperature changed, maybe how precipitation changed. We can see how atmospheric chemistry changed. So when the ice forms, the ice traps air bubbles. And when we take these ice cores out, we can run them on a mass spectrometer and we can measure the chemistry of the gas bubbles. And that tells us directly what the composition of the atmosphere was 800,000 years ago.
Wow.
So we know, for example, that CO2 has never been as high as it is today in the atmosphere for the last 800,000 years. In fact, we think that the last time carbon dioxide was this high was 3.5 million years ago. Climate was a lot warmer. Sea level was a lot higher, and we didn't have big ice sheets like we do today. We didn't have Greenland, we didn't have Antarctica. So things were different back then. But it just means these ice core records are an incredible archive of climate.
So how do ice sheets influence our current weather and climate systems?
Well, we talked about how ice sheets influence sea level.
Yeah.
So by melting, sometimes melting quite rapidly, they can contribute quite a lot to sea level rise. And in the past, for example, at the last glacial maximum, the sea level was about 130 meters lower than today because of that.
Because there was so much more ice on land.
Right.
Most of that was in North America, actually. About 80 meters of that was North America.
And some rapid changes, for example, in North American ice sheet, led to rapid changes in sea level. We had a period called Meltwater Pulse 1A, where we had about 15 meters of sea level rise in just 3 centuries.
It's more than 10 times the current rate of sea level rise. So it's not true to say we haven't had rapid changes, climate changes or sea level rises before. We just haven't had such a fast change in atmospheric CO2 before as we're having right now on that kind of scale.
Okay. And at that point then, when you're talking about this massive sea level rise in the past, what would have contributed to that?
So we were right in the middle of a period called the last glaciation, and this was taking us out the last ice age. So there's some very big changes in greenhouse gases, and also changes in the orbit of the Earth. So it's very warm. But really what caused these rapid changes in sea level are instabilities that were triggered. So the ice sheets were slowly melting, and then there was some trigger of some instabilities due to the geometry of the ice sheets. And some of it occurred in North America and some of it also occurred in Antarctica. And this is what we were talking about earlier, these instabilities in part of the ice sheets that rest below sea level.
Okay.
Yeah, that particular change was probably actually an instability in the continental interior of the ice sheet. That's something Lauren's worked quite a lot on, and I've looked at the climatic effect of the change in the ice sheet. So we have this slow change in climate that causes a slow change in the ice and then a threshold cross, just like that.
Wow.
Right? The bottom drops out of the ice sheet. There's a huge melting event.
About collapsing. Like that's what you would define as collapsing an ice sheet.
So essentially what happened at this time was you had two big ice domes in North America. Mm-hmm. And they were slowly melting away. And you had an ice saddle bridging the two mountains, if you like, of ice.
Okay.
And then as this ice saddle lowered progressively, it crossed a threshold and started melting very quickly. It's very simple physics, actually. It's amazing that we didn't discover it sooner. Mm-hmm. But once you cross that threshold and the melting suddenly happens very quickly, you get almost this flood of water to the North Atlantic and to the Arctic Ocean, mostly. And then that's what I've been looking at with our climate models. We can put that meltwater into the oceans in those places to see then what the effect on ocean circulation and on climate is, to try and understand not only how the ice sheets changed, but then what the effect of the change in the ice sheet is.
Okay.
So how long does it take? So if, for example, the Greenland ice sheet melts, how long does it take for the southern hemisphere, for example, to notice the effects of that change in the ocean circulation? The Atlantic circulation.
The change in the Atlantic circulation. It depends a lot on actually where the melting takes place in the first place. So, for example, in the Atlantic, we have this large ocean circulation we call the Atlantic Meridionnal Overturning circulation. It's a large-scale circulation, right, where we have the northward flow of relatively shallow warm water from the equator towards the pole in the Atlantic. And then at high latitudes, so when we're starting to go past the UK, heading north, that warm, shallow water loses its heat because you're heading into the cool poles. Mm-hmm. It loses its heat, so it becomes more dense, right? Density and salinity are the two things. Salinity and temperature are the two things that affect density. So it's losing heat, so it becomes more dense. And because that water's become more dense, it sinks. And then it returns at depth in the Atlantic. It heads south towards Antarctica. Okay. This is the Atlantic Meridionnal Overturning circulation. Yeah.
Cool. Okay.
And because it's a density-driven circulation on such a large scale, if you put fresh water in at the high latitudes into the Arctic Ocean, into the North Atlantic, say around Greenland or around North America for the last glacial maximum, or around the Nordic seas, then you are affecting the density in those really critical regions for driving this ocean circulation. Mm. So you've made the waters less dense, and so you stabilize the water column. You stop the mixing that's happening vertically, or at least you reduce it. And if you reduce that mixing, then you get less of the sinking, and then you weaken this overturning circulation. Okay. The consequence of that is that you bring less warm water northwards, so the northern hemisphere starts to cool, right? Yeah. And then because you've taken less warm water out of the southern hemisphere starts to warm. Mm. This circulation takes a few centuries to properly wrap around. So if you had a change in the North Atlantic, say from melting of the Greenland ice sheet, you could start to see some changes in the southern hemisphere within a few decades maybe, but really you're probably talking about a couple of hundred years before you're really starting to see those effects in the southern hemisphere around Antarctica. Yeah.
Wow.
Do you think this circulation can collapse at some point?
Absolutely. It can. But will it? No, I don't think so. I think that's unlikely. There was a time when our models, some of our climate models did suggest that it might, and that northern hemisphere could actually get very cold in response to CO2 rise. Now we don't think that's going to happen. We do think it will weaken. There are signs that it's weakening already. But we are struggling to put that in the context of these larger changes that we know about. What we do know is that if things carry on warming, then there's more melting going to happen in Greenland. That's going in at exactly the wrong place for affecting this ocean circulation. It's just going to potentially have quite a powerful effect over the next 1,000 years. So the question is, how fast does the Greenland ice sheet respond?
Yeah, that's a big question at the moment. Yeah, so we know, for example, that just due to warming, there's an increase in the melt at the surface of the Greenland ice sheet. What we know a bit less is when this melt sort of trickles through the ice sheet to its bed, how it affects how the ice slides on the bed. We think it could accelerate, but we don't really have very good observations of what happens right underneath those kilometers of ice and how they flow on the bed. So, I mean, if the whole of the Greenland was to disappear, this would rise sea level by about 7 meters. But this would take thousands and thousands of years.
It's hard to predict. It's hard to predict because we don't know how governments are going to change their emissions policies, how we are going to find innovative technological ways to re-engineer our climate, or if that will even be allowed legally. So it's very difficult to predict how fast Greenland will melt in the next few hundred years. But the potential is certainly there. The event that Lauren talked about before, Meltwater Pulse 1A, happened about 15,000 years ago. And as she said, it was about 15 meters of sea level rise in 350 years. So that's about double of what's left on Greenland now. But it had a huge cooling potential for climate. It's certainly putting that much meltwater in the North Atlantic and Arctic Ocean. Lauren and I have run simulations where we put about 7 meters into the Arctic, North Atlantic Ocean, and we got several degrees of cooling in the North Atlantic. And the Atlantic overturning circulation weakened by about a third, but it didn't switch off. It didn't need to switch off to have such a strong influence on climate. So I don't think we need to worry about the circulation collapsing, as some disaster movies have hypothesized in the past, if you've ever seen The Day After Tomorrow. Probably not going to happen, but it potentially has happened in the past. We think it happened during the last deglaciation, potentially. The point really is that it doesn't need to collapse to have a big impact.
Okay.
So we're learning about how these effects on the ocean circulation take time, a lot of time. Are there other ways in which ice sheets can have more immediate impact on our climate systems?
So the effect on the ocean circulation is a slow control. It can take decades or centuries to fully reach its effect. But there's also a fast influence of ice sheets. The influence on the atmospheric circulation can be pretty much instantaneous. Lauren's run some simulations in the past looking at that.
It is sort of, the atmosphere reacts much faster than the ocean, but it reacts to the shape of the ice sheet. So having a big ice sheet covering the whole of Canada, it kind of creates like a very big white mountain over a whole continent. And that displaces the atmospheric circulation and also where the storms will go over the North Atlantic and into Europe. But actually, the change in the shape of the ice sheet is very, very slow. So those changes in atmospheric circulation will tend to happen on timescales of centuries or millennia.
Okay.
Yeah, so it's interesting because the impact of the melting, that's a very fast control from the ice sheet. The melting can happen quite quickly, the change in the melting or where the meltwater goes, because you can imagine as the ice sheet is melting, it's changing its shape. So the watersheds change. So the direction that the rivers of meltwater might take change. That can be quite fast in terms of getting that effect into the ocean, but then the whole effect on the ocean can take quite a while. Whereas in the atmosphere, it's a slow change in the ice sheet that's important, but then once it has happened, potentially when you've crossed a threshold, then the effect on the atmosphere is actually quite rapid. And it can affect, like, for example, the jet stream and the track that the storms take across the Atlantic and hit northwestern Europe. So it can be very important for weather events in that sense, atmospheric circulation. And again, it's possible that we're talking about threshold events. So if the ice sheet, this was probably more important for the last deglaciation than it is now. When there was an ice sheet over North America that was maybe 4 kilometers thick, there would have been a threshold in that elevation where the atmospheric circulation was deflected north or could take its normal path, right? And so it might be a slow change in the ice sheet, but it is quite a quick moment where it goes from one side of that threshold to the other side of the threshold, so that the jet is either split either side of the mountain or can take its normal path like it does today. So it's it's a fascinating
It is, yeah.
subject to try and understand. And then you also have the feedbacks on the ice sheet itself. So Lauren talked about these marine ice sheet instabilities where changes in the ocean temperature influence the stability of the ice sheet. Well, ocean circulation is very important for that, because if you change the ocean circulation, you can change, maybe because of melting ice sheets, then you can change which currents are going near the ice sheet, and you can change the temperature of that ambient water. And so then you are influencing the ability of the ocean to melt the ice sheet where it's reaching the ocean. So it's all interrelated.
Yeah.
You change the ice sheet, you change the ocean, you change the atmosphere, you change the ice sheet, and they have huge climate forcing potential. They're just juggernauts of power.
Okay, so how do you think the sea level will be in the future? What are the projections of extreme sea level rise if we continue business as usual, emitting the same amount of greenhouse gases?
So that's an interesting question. So if you think of projection of sea level, you've got different components. The main one today is from the thermal expansion of the ocean. And then you've got...
So that's when things get warmer, they expand.
The ocean getting warmer, it'll take more volume and therefore rise sea level. And then there's the contributions from the ice sheets, which is the much more uncertain part of the projections. If you put it all together, I think at the moment we think 1 to 2 meters of sea level rise by the year 2100 is possible. But there are also some of my colleagues that have suggested larger than that, maybe 2.5 meters. If you have instabilities in the Antarctic ice sheets triggering a runaway ice loss.
Yeah, and to put that into context, 1 to 2 meters would displace 100 million people. So that's a huge number of lives affected, and you can imagine economically and politically. Again, there's a lot of potential to cause disruption in these vast sheets of ice.
And there's even more uncertainty if you think beyond 2100. And so maybe, most people might not think very much of the future beyond the next 100 years, but we need to know this for planning infrastructures that take a very long time. If you think of nuclear power plants, for example, the timeline of projects is more than 150 years. And they're very interested in knowing about the extreme sea level rise that maybe is unlikely, but plausible.
You'd be surprised how many nuclear power stations are built near the sea.
Well, I think in the UK there are about 9 at the moment. Yeah,
That's crazy.
9 that rely on coastal flood defences.
Really?
So they need to know a lot about the sort of extreme.
Do they use the seawater as a resource? Is that why you get so many?
Yeah, they use the seawater for cooling.
Yeah.
Oh.
So in terms of the running of the power plant, it makes sense, but it also means that you have to have a pretty good idea of what's going to happen in the future.
Yeah, exactly. So by the year 2300, for example, then we know much less. Some people have suggested, I think, 15 meters of sea level rise,
Which is quite extreme, but
Yeah, if we're thinking of how many people will be displaced on that scale, like, where would we be?
I think it's interesting here, isn't it? Because there are two different questions. There's what is the most likely sea level change, but then there's what could be the most extreme? Because the most extreme could be very unlikely, but extremely dangerous. And that's a really difficult one to quantify because of these instabilities, which we don't have observations for now, which we have to look at the past for. We have to look at this period when we went from the last glacial maximum to present. We have to look at how those ice sheets evolved, and how Antarctica changed, how Greenland changed, and how North America changed. North America was a bigger ice sheet than Greenland, but behaved in a very similar way, similar kind of latitude. The one that was over Europe is in a completely different place to Antarctica. It's in the northern hemisphere, but it's a marine ice sheet. So it can give us clues as to how the marine ice sheet changes over time, and therefore the mechanisms, the processes that we need to be looking out for and being able to understand and predict with our models that are relevant for Antarctica. Because the problem with Antarctica is there's a huge ice sheet there. So there's not a lot of evidence for what happened in the past. Whereas over Europe, over North America, we've got the evidence from the geology. We can see what the bedrock looks like today. So we've got all these different variables that we need to be able to understand it, to be able to simulate its behavior, to then take that understanding and use it to inform our knowledge of what's going to happen in the next few hundred years.
Yeah, and we actually have a big project starting now. It's going to be maybe up to 7 years. Or we're going to work directly with statisticians to better relate what happens in the past to what could happen in the future. So using some artificial intelligence techniques to use the information we have on the evolution of past ice sheets to directly improve our models of climate and ice sheets and use them in the future to project extreme sea level rise.
Yeah, it's a big team of people, about 8 people going to be working on this directly, and then obviously with partners in industry who are interested in sea level rise, who are feeding back to policy change. Important people.
And we might interview you in the future again.
We can give you some answers.
more.
We can give you some answers to the outstanding questions. Yeah, it's a fascinating topic.
Yeah, it is.
Definitely. Just like another question, because you've been talking about policy and how this kind of feeds back and the balance that you have between giving a realistic estimate of future projection and then also indicating how extreme the situation could be. How do you find like that balance when you're trying to talk to people who are actually decision makers or have power to take it on board? Like, what's the kind of balance that you have to make?
Well, interestingly, the Environment Agency, they're the ones who really take these projections and then inform everyone who needs to know about it, like the nuclear industry, transport industry. And they don't know at the moment how to use information on projection of extreme events and how to communicate it. So we'll be working with them and trying to find out better ways to communicate with each other and use the information.
And develop tools to handle the information. It's very difficult when you've got this envelope, this window of uncertainty surrounding an event. You know, do we care about if it's a 1 in 100 year event, a 1 in 1,000 year event, a 1 in 5,000 year event? Probably depends on how extreme it is, how dangerous it could be. Everybody has different thresholds. But at the moment, in this field of climate and glaciology, we haven't been able to handle that uncertainty quantitatively enough. So we haven't been able to pin down the numbers well enough that somebody who's not expert can use that information. And that's what this project's all about. It's about using, as Lauren said, artificial intelligence, very novel statistical techniques, together with the mechanics, the physics, to be able to come up with some very robust information that is useful and real and not just an opinion.
Cool. Sounds great. We look forward to
We're
it.
excited about it. We're very excited about it.
Good.
Okay. Thank you for having us.
Thank
Thank you very much.
Thank you very much.
Stay tuned for upcoming episodes and follow us on Twitter using @theclimatepress.
And if you want to get in touch with us, please visit our website, theclimatepress.com.
See you soon. And remember, make love, not CO2. This week's episode was co-produced with Tom Wood. Theme music for the show was written and performed by Paloma Trascasa Castro and Marcos Arribas. And exciting news for you listeners, The Climate Press is now available on other podcast platforms like Spotify, Apple, Google, Breaker, and Radio Public. You can go to our website for more details.